All right, campers, we have gone through a lot of wave properties, and today we should be finished with wave properties of mechanical waves. Now, I got nothing really exciting for this demonstration. I can't even act like an idiot like I've tried to do, like, woo, with the wave. But we'll try and get through this as painless as possible. You can see here what we're going to talk about. We're going to talk about applications of the Doppler effect. In other words, the Doppler effect has real-world applications other than meow. Then we're going to talk about reflection. I'm actually going to kind of tie that into the Doppler effect and then give it to you just straight out. And then two other terms, refraction and diffraction. Or diffraction. Now remember, all of the properties we've talked about for mechanical waves, many of them we will see again when we talk about electromagnetic waves. So let's get right into it. Applications of the Doppler effect. One day, you are going to have your license, and maybe you will be driving this hot red sports car, and maybe some of you will become police officers looking for the other ones in the hot red sports car. And the way a radar works, police radar transmission for speeding, is the Doppler effect. Now, what exactly is taking place in this picture? I'm going to explain, and then we're going to go into a couple of other pictures. Now, police radars use microwaves. Yeah, just like in your microwave oven, but a different kind of frequency. We'll talk about that later. Now, these microwaves have specific wavelengths and specific frequencies. So the police send those radar waves out, as you can see, here and here and here. And now this car that's going towards you, the waves hit the car and reflect. Yeah, I told you I'm going to tie it in. Reflect or bounce those waves right back off to the police officer and his radar detector. Now, the radar detector does all of the work for the police officer, and what it can do is measure it knows the frequency and or the wavelength of the waves going out. The waves bounce off the car and come back, and then the radar detector gets to do all of the internal programming, figuring out how fast those waves are coming back, or more specifically, what the new observed wavelength and the new observed frequency are, and we can tell if you're speeding. So this little formula right here is what the radar detector does. The police officer says, oh, all right, I'm going to try and detect people going towards me or away from me, and the frequency of the original frequency plus the frequency of the detector, or the other way around, subtracting if they're going the opposite direction. So again, the police officer doesn't need to do any of that math, but it is real-life Doppler shift. It is a shift in the apparent frequency of the observer, which is right here, FO or FO, the observer. Now, this is a little bit easier for you to see. Now, there are three different ways that the police officer can be figuring things out. The police officer could be stationary and people could be driving towards him or away from him. The police officer could be driving towards you. You could be going towards the police officer. You could be going away from the police officer, etc. It doesn't really matter which way we're doing. No matter what, the Doppler effect is a change in apparent frequency due to the motion of an object compared to its observer. So the radar detector can pick up a change in frequency, a higher frequency, a lower frequency, a higher frequency or a lower frequency compared to if just regular what it is putting out, its regular frequency. Now, the microwaves travel at a specific velocity using that wave equation, velocity equals frequency times wavelength. Just like the speed of sound, we said we'll always pretty much say it's 343 meters per second. The speed of the microwave is constant, always the speed of light. That is 3 times 10 to the 8th meters per second. So we know that, and the radar detector knows that, so we can pick up that apparent shift in frequency. Now, some of you or some of your parents or friends may have radar detectors. My opinion, those don't work. Well, why not, Mr. Rose? Why don't those work? It is true, the radar detector detects the radar. So, if I'm driving my car and this is my radar detector, well, in order for my radar detector to detect the police radar, that means it's already hitting my car. So I detected the radar, the police also detected me, so they may or may not already know that you are speeding. I don't believe in them. I just believe that you should drive responsibly and safely and observe all traffic laws to the best of your ability. Now, Doppler radar also is for weather. I'll go through this a little bit faster. Now, if you watch the news later today, or even just on your cell phone, like, hey, what's the weather? You can look at the Doppler radar. It does the exact same thing the police radar does. Here you have two different things. We'll talk about the velocity first. Weather patterns, clouds, rain, etc., are either going towards you or away from you. They work the exact same way. The radar sends the signal out. If the weather system is moving away, when it bounces back, we get a different change in frequency. You should know what that is. If it's moving away from the observer, would it be a higher frequency or lower frequency? You know what? I'm not even going to answer that. I'm going to let you answer that. If it's moving towards you, the same thing. So we can figure out what that is. Next is this reflectivity. Well, this is not really the Doppler effect so much, but it is a wave transmission and a wave property. So here I have another picture of what's going on. We can figure out the velocity, and that's what these pictures are, of the system going away or system going towards. The radar detector goes out. I told you I'm going to leave you to figure out. If it's going away, we see a bigger wavelength, so that's a shift in frequency. Waiting for it. It's a shift in higher frequency. Or if I see, I lied. Lower frequency. My fault. Or if it's going towards you, you see all these waves, really small wavelength, higher frequency. When I put my hand up, you can't tell that I'm giving you the answer. So that's one thing. Now, if you've ever been a big empty room, it's a good echo room. You go, hello, 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 hello. And echoes are something we're about to talk about. But that means the waves bounce off really easily. Now, if I go back, this reflectivity, based on what the weather system is doing, snow, sleet, rain, hail, sunny, the radar that we send out gets absorbed differently for different particles. For example, water is a different consistency than, say, snow and ice. So based on how much of the wave gets absorbed by that system, just like an empty room compared to a full room. If you have lots of people in the room and lots of stuff and like soft things, carpet and pictures. Also, we spoke about singing in the shower. I'm singing in the shower. You sound better because the water absorbs some of your voice. The same thing. So the radar that sends out these signals based on what gets absorbed and what gets reflected back, we can tell what's going to end that system. And that's why we have these percentages of like, it may be 50% rain, 50% hail, 50% sleet. That's 150%. Figure that out. But we don't really know. It's kind of a guessing game on what's being absorbed now and what may hit us later. So that are applications of the Doppler effect. Now, the next stuff is actually going to go through really fast. Wave reflection. We all know what reflection is. And wave reflection is easiest when I think about light. If I look at myself in the mirror, I see myself in the mirror. That's a light wave reflecting. An echo is if I make a sound, it goes and hits off some surface and bounces back. Now, we'll talk about this a little bit more with light, but the angle of reflection. All waves have this, and that's why I chose this picture. It's kind of at an angle. If I put a line right through, a perpendicular line, the angle of reflection means whatever the angle that wave comes in, it bounces back at the same angle. But essentially the reflection of any wave is waves go in, hit something, and bounce off. And an example of that is an echo. I yell, hello, into a cave. Hello. And then I hear that echo back. That means my wave, my sound wave, went into that cave, bounced off the wall, and came all the way back. Just like all those reflection examples I just showed you. Now is a new term, refraction. Refraction is easier to see with light, but I'm going to talk about it with a mechanical wave. By definition, Refraction is just the bending of a wave when it changes a medium. Now, it's a little bit harder to talk about with mechanical waves, but essentially the light bends because the wave either speeds up or slows down. So, when I have said the speed of sound in air is 340 meters per second. If you were yelling into like a pool, like you're underwater, I'm on top and I'm loud, and I'm like, yo, get out of the pool! If you were underwater, you would still hear me. I'd sound different, and my wave speed, the speed of sound, would hit the water, and some of it would get absorbed, some of it would penetrate, and the speed of sound in the water is different. It's way faster. So, the same thing, like if you yelled out of the pool, and all those bubbles came up, I might hear it. It would sound churned and weird, but the speed of sound would slow down as it goes from the water to the air. It's easier to see this, and look, I have an example of this right off the top of my head. If you think about cars changing mediums, so like from pavement to sand, it's harder for the car to drive on the sand, so the car slows down if it's at an angle. If it's straight on, we can't see it. The car still slows down because, the wheels are turning in the sand. A real life example, this isn't how I hurt my arm, but we can picture it. Picture me rollerblading, because that's how I hurt my arm, and all of a sudden I'm on pavement, and then my one skate, like the left skate, hits grass. That slows me down, so my body would turn, and you would turn into the slow. See how it slows down and it turns into that? And if you lose your balance, you'll bam! Break your wrist. So, refraction is just the bending of any wave. I'll show this to you easier with a light wave. But refraction is any wave that's bending when it travels from one medium to another, and that wave either speeds up or slows down. Essentially, if the medium is thicker, the sand is thicker than the pavement, right? I could like grab the sound. Thicker mediums slow the wave down. Now, this is the same thing. Sorry. This is just out of an old textbook. That exactly what we're talking about, a top view, when like a wheel hits one wave to another. When a wheel hits like sidewalk to grass, it slows down. Now, this is light waves we're going to talk about next. That's actually why I put this up here. We can see that the light wave, as a lot of you already mentioned, based on my last video, the light waves slow down as they hit the water rather, and they bend. They bend when they change mediums. We will get into that next week. Last one, diffraction. Diffraction is when a wave bends around an obstacle, right? So again, the best example is, lots of us do this. When we shout, we put our hands here like this. So as soon as I'm done yelling, the sound waves spread out outside of my hand. In a room, if I'm yelling my sound waves, there's a door, but you can hear the sound on the other side of the door, even if you're not standing right in front of it, right? So again, let's pretend this is the door so you can't see me. I'm hiding, but I'm talking, hey, what's going on? The microphone still picks me up because my voice, the sound waves, can bend around this obstacle. Here's just a quick visual of it. So here are some waves that are coming through. Here's this little obstacle like the door. And then the sound waves, in this case, these aren't really sound waves. This is actually like, would be water. But the sound waves can then diffract and bend around the obstacle. That is literally everything we have to do about mechanical waves. I hope you have learned something. I hope you have, trying to think of some wave pun. I hope you have a wavy good time. These are bad. Anyway, that's all we have. By all means, if you have any questions, shoot me an email. Thank you for your attention. As always, if you're watching this on YouTube, feel free to like, comment, or subscribe. And you will see me next time when we are talking about electromagnetic waves.